We will continue with protein functionality. Protein functionality describes what the protein does from our point of view. Proteins generally have a great influence on the sensory properties of foods. The physical and chemical properties influence the functionality of proteins in food systems during processing, storage, preparation, and consumption. Properties that govern functionality include protein size, shape, amino acid composition, and sequence. Also, net charge and distribution of these charges. Hydrophobicity is important. Also, the levels of protein structures, chain flexibility, and ability to interact with other food components such as lipids and carbohydrates. The functional roles of various proteins in different food products are listed in this table. Proteins must show good and multiple functionalities in order to perform well in food systems. There is no single protein exhibits all the functional properties listed here. Especially proteins of animal origins, for example, the muscle proteins, milk proteins, egg proteins. So they are widely used in fabricated foods. These proteins are mixtures of several proteins with wide-ranging physicochemical properties. And they are capable of performing multiple functions. For example, egg white protein. So egg white protein has multiple functionalities such as gelation, emulsification, and foaming. So which make it a highly desirable protein in many foods. Okay. And proteins have hydration ability. So what's hydration ability? So it's the ability of proteins. So when we say hydration, it's the ability of proteins to dissolve in water or to attract water. Okay. Because of that hydration ability, they play several important roles in food systems. As an example, one of these is the capability to form a gel. Gel is a network of protein strands trapping water that results in a firm structure. Okay? And water molecules bind to several groups in proteins. So these groups include charged groups. Okay. And then backbone peptide groups. And the amino groups. Hydroxyl groups. And non-polar amino acid residues. Okay? So this water binding capacity is also sometimes called hydration capacities. And these hydration capacities of various polar and non-polar groups of proteins are given in this table. For example, amino acid residues with charged groups bind about 6 moles of water per residue. And here we have an uncharged polar amino acid residue which binds about 2 moles of water per residue. And the non-polar groups bind about 1 mole of water per residue. They have different hydration capacity. So when we look at this table, we see that this hydration capacity is related to amino acid composition. So the greater the number of charged amino acid residues, the greater is the hydration capacity. Okay, as you see here, the charged amino acids binds more water. Especially charged groups are important in water binding. Okay, let's move on. So why this hydration is important? Let's see. So firstly, how we define the hydration. So the water binding capacity of protein is defined as grams of water bound per gram of protein. So it can be calculated from its amino acid composition using this equation. So Fc is the fraction of charged amino acid residues, and Fp, fraction of polar amino acid residues, and Fn, fraction of non-polar residues in protein. So remember, when we say residue, we mean amino acid residue. Actually, they are amino acids, but when they are in a polypeptide chain or in a protein, we call them amino acid residues because they are part of a protein. Okay. So this hydration ability of proteins are very important because this hydration is necessary for their solubility in water. And the solubility of a protein is the most important functional property because the protein needs to be soluble in order to be applicable in food systems. And also other functional properties like emulsification, foaming, and gelation are dependent on the solubility of proteins. Okay? So it's important. Let's see the solubility. Okay. Solubility can be described as when equilibrium exists between hydrophilic and hydrophobic interactions. It represents the equilibrium between protein-protein and protein-water or protein-solvent interactions. Okay? So the major interactions that influence the solubility characteristics of proteins are hydrophobic. And ionic. So these hydrophobic interactions promote protein-protein interaction and result in decreased solubility. So when we have these hydrophobic interactions, we might have aggregation, and it might result in precipitation. Okay? Because solubility decreases. So on the other hand, ionic interactions promote protein-water interactions here and result in increased solubility. Okay? So these ionic interactions also called electrostatic interactions. Okay, let's continue. So based on these solubility characteristics, proteins are classified into 4 categories. So the first one is albumins. Those are soluble in water. An example can be serum albumin or egg albumin. And we have globulins that are soluble in neutral salt solutions at pH 7. Example can be beta-lactoglobulin. And glutenins, those are soluble only in acid at pH 2 or alkaline at pH 12 solutions. An example is wheat gluterin. And the last one is prolamins. And those are only soluble in 50 to 80% ethanol. An example can be zein. Also we have gliadins. Okay, here, especially the last two ones, glutenins and prolamins. So these are highly hydrophobic proteins. Okay, highly hydrophobic proteins. Let's continue. So solubility is affected by several conditions, especially pH. The solubility of a protein is related to the pH of the environment. pH is the most important factor when it comes to the degree of protein solubility. When solubility is plotted against pH, most food proteins exhibit U-shaped curve. So like this one here, U-shaped curve. Minimum solubility occurs at about the isoelectric pH of proteins. Okay, minimum solubility occurs here. So there is no net charge at isoelectric points. But it should be remembered that even though a protein is electrically neutral at its isoelectric point, it still has positive and negative charges, but these are equal numbers. So number of positive charges equal to number of negative charges at isoelectric point. Okay. But at pH values below and above the isoelectric pH, proteins carry a net positive or net negative charge. So when the pH is above isoelectric point, the net charge of protein is positive. So here, when the pH is below isoelectric pH, net charge of protein is negative. Sorry, it's already written here, positive and negative. Okay. So what promotes solubility? Electrostatic repulsion and hydration of charged amino acid residues promote solubilization of the protein. So the occurrence of minimum solubility near the isoelectric pH is due to the lack of electrostatic repulsion. Okay. which promotes aggregation and precipitation via hydrophobic interactions. Okay. Okay, minimum solubility at isoelectric point. That's the general rule. But you know, food is a complex system. There are always some exceptions. So here, some food proteins can be highly soluble at their isoelectric pH. For example, beta-lactoglobulin and bovine serum albumin. They are highly soluble at isoelectric pH because these proteins contain a large amount of surface hydrophilic residues. So these are the exceptions. But the general rule is minimum solubility at isoelectric point or isoelectric pH. Okay. So by knowing that pH solubility relationship, some food processes can be designed in industry. For example, here. So this figure is a typical industrial process. It's for the isolation of soy protein from soybean. So protein extraction from plant sources is done based on this pH solubility behavior. So let's see. Soy protein is highly soluble at, it's highly soluble at alkaline pH, like pH 8 to 9 here. So to increase the solubility of that soy protein, the extraction is done at this pH using an alkali solvent. So the soy protein is solubilized in that alkali solvent, then it's centrifuged, and now the proteins are here in the supernatant part. Then the pH is adjusted to acidic pH. So what's the reason for that? So we make the environment acidic because we want to precipitate and separate the protein. Because they have an improved solubility at alkali solutions, but decreased solubility at acidic solutions. Then it's centrifuged again, and soy protein isolate here obtained by spray drying. Okay, so pH solubility relationship is important. By knowing that, many processes can be designed in food industry. Okay. Let's see another factor which affects solubility of proteins here. The solubility is also influenced by ionic strength. What is ionic strength? So ionic compounds like salt, when dissolved in water, dissociate into ions. So these are different salts. Here, ionic compounds. So the ionic strength of a solution is a measure of the concentration of the ions in that solution. The concentration of the salt, for example. So we can change ionic strength by changing the salt concentration. So when we do that, when we change the ionic concentration, the solubility of the proteins will change. So let's look at the first graph here. It shows the effect of salt concentration on the solubility of proteins. Here y-axis is the solubility and x-axis is the salt concentration. It's increasing that way. So as you see here, the solubility of proteins changes as a result of change in salt concentration. But what are these terms? Salting in and salting out. So as salt concentration increases, which means as ionic strength increases, the solubility of a protein increases. It's called salting in here. Solubility increases. And as the salt concentration is increased further, the solubility of the protein begins to decrease until a point where the protein is precipitated from the solution here. And it's called salting out. So what happens? So at low ionic strength, generally below 0.5, the ions neutralize charges at the surface of proteins and solubility increases. The water molecules, which are polar, they tend to arrange themselves around the protein molecules due to the electrostatic interactions. So salt molecules stabilize protein molecules by decreasing the electrostatic energy between the protein molecules, so which increases the solubility of proteins in water. So we decrease the electrostatic interaction between protein molecules. So water goes between protein molecules and form electrostatic interactions between protein and water. Okay, this increases the solubility of proteins in water. Because if there are like strong protein-protein interactions, the aggregation of protein molecules can occur and it might result in precipitation. So protein-water interactions increase the solubility. So it happens at low ionic strength, at low salt concentration. So how can we explain salting out? Again, in an aqueous environment with a high ionic strength, high salt concentrations, the salt molecules compete with the protein molecules in binding with water. So the availability of water molecules becomes limited as most of them are used up by salt ions. So we can say here protein is dehydrated. Okay, because of this dehydration, protein molecules come together and they might aggregate and precipitate. Okay, that's the reason for decreased solubility at high salt concentration. Okay, this protein solubility also depends on salt type. Here, like there are different types of salt. They can be used for different purposes. For example, if you want an improved solubility, you can use sodium chloride to salt in your protein. If you want to separate your protein from a solution, then you can use an ammonium sulfate. See here the solubility profile against salt concentration. This is the molar. Okay, let's move on and see other functionalities. So there are several natural and processed foods which are either foam or emulsion type products. They are unstable unless a surfactant or suitable amphiphilic substance is present at the interface. So this is interface, right? Between these two phases. This formation and stabilization of foams and emulsions requires the presence of a surfactant, okay, or an amphiphilic substance that can effectively reduce the interfacial tension between these two phases. It can be an air or oil and aqueous phases, okay? So remember, some small molecular surfactants such as lecithin, monoacyl glycerol can be used as an emulsifier in food industry. So proteins can also be used for that purpose. Proteins are amphiphilic molecules. So here, amphiphilic. So that means they have both hydrophobic, nonpolar, and hydrophilic polar regions, right? So proteins migrate spontaneously to the interface between these two phases. So they reduce the interfacial tension between these two phases. Interfacial tension is the force of attraction between the molecules at the interface of two fluids or two phases. Let's continue. Here you see the modes of adsorption of protein at the interface. So there are three distinct configurations: trains, loops, and tails. So the relative distribution of these three configurations depends on the shape of the protein, the conformational characteristic of the protein. If there's a greater proportion of train, the protein binding at the interface will be stronger. So this will easily lower the interfacial tension. So distribution of these configurations are important. So when adsorbed at interface, protein forms a highly viscoelastic film at interface. A highly viscoelastic film which has the ability to withstand mechanical shocks during storage and handling. So surface hydrophobicity is important in protein adsorption at interface. Here you see protein in solution unfold and reorient at interface. Then it adsorbs at interface and form a viscoelastic film. So desirable surface active proteins have three attributes here. So the first one is the ability to rapidly adsorb to an interface, and then ability to rapidly unfold and reorient at an interface. And the third one is an ability once at the interface to interact with the neighboring molecules and form a strong cohesive viscoelastic film that can withstand thermal and mechanical motions. So what about the concentration of protein at interface in this viscoelastic interfacial film. It's about 20 to 25%. Its weight per volume of the solution, protein concentration. Okay, let's continue. Let's see the emulsifying properties of the proteins. Foods such as milk, soy milk, egg yolk, butter, margarine, mayonnaise, salad dressing, sausages, cakes, those are all emulsion type products where protein plays an important role as an emulsifier. Emulsions consist of two liquids that are immiscible, where one of the liquid is dispersed in the other in form of like small droplets, as you see here. So we have a dispersed phase. This is the dispersed phase. And this is the continuous phase. Emulsions can be classified according to the distribution of the oil and aqueous phase. A system where the oil droplets are dispersed in the aqueous phase, continuous phase, is called oil in water emulsion. Examples are like mayonnaise, milk, cream, some sauces. So the opposite of an oil in water emulsion is the water in oil emulsions. So these are the common emulsion types, but there are also some multiple emulsions in food industry, like oil, water, oil, or water, oil, water. So these are called multiple emulsions. The emulsifying properties of food proteins are evaluated by several methods, such as size distribution of oil droplets formed, emulsifying activity, emulsifying capacity, and emulsion stability. Emulsion stability. So how do we measure emulsion stability? Drastic conditions such as storage at elevated temperature or separation under centrifugal force is often used to evaluate emulsion stability. It's done like that because protein-stabilized emulsions are often stable for days. Therefore, a detectable amount of phase separation is usually not observed in a reasonable amount of time, when especially samples are stored at atmospheric conditions. A common centrifugation technique involves centrifugation of a known volume of emulsion in a graduated centrifuge tube at around 1300 G for like 5 minutes or 15 minutes if we increase the gravitational force. The volume of the separated cream phase is then measured and expressed as percentage of the total volume. The volume of cream layer over total volume of emulsion times 100. Okay, stability can be expressed as percent volume of cream separated. So if that number is high, that means it's not a very good stable emulsion. So emulsifying capacity is another method to evaluate the emulsifying properties of proteins. So it's the volume of oil that can be emulsified per gram of protein before phase inversion. So what's phase inversion? We said we have, for example, oil in water emulsion. So a change can be occur from oil in water emulsion to water in oil emulsion. So that's phase inversion. Something like that, or the opposite. So it involves addition of oil, or it can be a melted fat at a constant rate and a constant temperature to an aqueous protein solution in a food blender, as you see in that picture. Usually a dye is added to the oil, so phase inversion can be observed easily. Okay. Another method is emulsifying activity index. It's the interfacial area created per unit mass of protein. So the turbidity of an emulsion is given by T. Let's say, as an example, we have oil in water emulsion. We have 10 milliliter oil and 90 milliliter water. Then the volume of fraction will be 0.1 because total is 100 milliliter solvent. So you need to measure the absorbance at 500 nanometer. This is the path length of the cuvette you use. Then you can calculate the T. So put T here. So this will become 0.9 because volume fraction of the oil is 0.1 here. And if you know the weight of the protein in the emulsion, so you can calculate the emulsifying activity index. Okay, that's it. So there are many factors affecting emulsification, such as pH, ionic strength, temperature, sugars, etc. Also the type of protein, the composition is important, and we said protein solubility is an important property, and it's related with hydrophobicity, surface hydrophobicity. Here you see in this graph the interfacial tension decrease, right, as we increase the hydrophobicity, and emulsifying properties increase. We get a better emulsion when we increase the hydrophobicity. So remember, albumins and globulins, they are highly hydrophobic proteins. So they have higher surface hydrophobicity. So they can lower the interfacial tension at the interface. On the other hand, emulsions show low stability at isoelectric point. So what can be the reason? Remember, at isoelectric point we have minimum solubility of proteins. That's why the emulsion stability will be low, because proteins cannot function well at isoelectric point. Proteins also stabilize forms by forming flexible cohesive films around the gas bubbles. So forms consist of a gas phase, a liquid phase, and a surfactant, which are proteins. So by bubbling, whipping, shaking, you can form foams. Foods made up by foams are whipped toppings, meringues, ice cream, or maybe angel cakes. So these are foams. Foams are formed through unfolding and absorption of the protein at the air-water interface. Film form around the air bubbles. So different proteins have different abilities to form and stabilize forms. For a protein to have a superior forming properties, it must possess high solubility in the liquid phase, as well as the ability of quickly forming a film around the air bubbles in the food system. So we can evaluate form properties by several ways. We can use different volume fractions of foam for our evaluation. Here it's given from A to E. A is the liquid volume, B volume of incorporated gas, C total volume of dispersion, D volume of liquid in foam, and E volume of foam. So let's see. So the forming capacity of a protein is the amount of interfacial area that can be created by the protein. It can be expressed in several ways, such as overrun or forming power. So overrun is defined as the volume of foam over volume of initial liquid times 100. Or as forming power, volume of gas incorporated in the liquid. So foam power increases with protein concentration. Up to a critical protein concentration. So in this table, you see different forming powers of different proteins. And foam stability. It refers to the ability of protein to stabilize foam against gravitational or a force or a mechanical stress. It evaluates the strength of the protein film. Okay. So these are all simple empirical methods. They do not provide fundamental information about the factors that affect foam stability, but they are useful to evaluate the forming of proteins. So what affects the foam performance? pH. Since repulsive forces are minimized at isoelectric point, foam stability is enhanced. But foam capacity is reduced, since most proteins have reduced solubility at their isoelectric point, and only the soluble fraction will participate in forming. Forming capacity is reduced. Okay? And salts. It depends on the salt type and protein type. Proteins are salted out with a given salt exhibit improved forming properties, or they can be salted in, depending on the salt type and protein type. Sugar can affect foam performance. So foam stability can be improved due to increase in viscosity of the solution. Sugar increases viscosity. So it will stabilize the foam by increasing viscosity. But again, it decreases foam capacity. So because of decrease in foam. Okay, improved foam stability with sugar due to increase in viscosity, but decreased foam capacity due to decrease in foam volume because of the increase in protein stability. So lipids affect foam performance. Polar lipids especially decrease foaming properties. Lipids are more surface active than proteins. They also have emulsifying properties. So they readily adsorb to the interface. So when they adsorb to the interface, they inhibit foam formation, especially polar lipids. So another functionality is protein gelation. Protein makes gels. What's the gel? Gel is a continuous three-dimensional network of proteins that entraps water. So protein gelation is a transformation of a protein from solid state to gel-like state. So if precipitation occurs, it's not gel anymore. So protein gels are made by treating a protein solution with heat, enzymes, or divalent cations like calcium or magnesium. You can use heat, enzymes, calcium or magnesium. So there are several ways. So you form a 3D cross-linked network structure, and it might involve some covalent and non-covalent interactions. Okay, there are protein-protein interactions and protein-water interactions. Covalent and non-covalent bonds. So covalent can be disulfide bond, and non-covalent can be like hydrogen bonds, hydrophobic interactions, electrostatic interactions. Okay. So proteins from milk, meat, egg, and soy have all been used in a variety of gels. So the gelling ability of proteins allows them to be used as binders, stabilizers, and thickeners in a variety of foods, such as like preserves, jams, confectionaries, gums, marshmallows, desserts, ice creams, puddings. Okay. First, proteins are unfolded, then aggregated in a three-dimensional network. If precipitation occurs, it's not gel anymore, okay? So protein gels made by heating are the most common type. So heat denatures proteins. So hydrophobic regions of proteins are exposed during denaturation, which cause aggregation. And after a certain time, you get a cross-linked 3D gel network, which is your gel. So this thermal denaturation can be reversible or irreversible. So we have thermoset reversible gels. So if it reverses fully or partially to the solution state on reheating, then it's called thermally reversible. Okay, reversible thermoset gels melt on reheating. They reverse fully or partially to the solution state from gel state, okay? So it's called thermoreversible gel. And as the name says, we have also thermoplastic irreversible gels. They are irreversible. So you thermally set the gel, it will form irreversible crosslinks. So when you reheat, it will not revert back to the solution state. Still, it will be in gel state, okay? Protein gels also made by using calcium or acids. So here you see some examples. For example, tofu is an example for calcium-induced gelation. And the casein gels, cheese, it's an example for acid-induced gelation. Also, there can be some pressure-induced gelations. High pressure reduces hydrogen bonding and promotes dissociation of water molecules. An interaction of water with nonpolar molecules creates gel network. There are opaque gels like egg white and transcoolant gels like beta-lactoglobulin. And there are several factors affecting gel performance. Molecular weight. Small proteins cannot form gels unless they are cross-linked via disulfide bonds. For example, proteins below 20,000 Dalton. 20,000, the molecular weight. They cannot form gel. So concentration is an important parameter, and pH is always important because it affects the solubility, and solubility affects the gel formation. And depending on the enzyme and salt type, the gel performance can be different. So they are important too. Okay, that's all for this lecture. Let me know if you have any questions.